Hello students, this video is a continuation of the modulo K counter problem concept. I was discussing the modulo K counter problem in the previous video and I had given a few basic examples of modulo K counter. Now in this video, I will explain another problem with respect to modulo K counter. The DFSM construction for a modulo K counter problem is done in 3 steps. First, we identify the number of states. Then we identify the start state and the final state, and once the start state and the final state is identified, we can easily write the transitions and design the deterministic finite state machine. The example question for this video is to construct the DFSM to accept strings of A's and B's having even number of A's and even number of B's. So this term having even number of A's and even number of B's is very important in the construction of the strings. This is also written as construct a DFSM to accept a language which consists of strings W such that W has got even number of A's and even number of B's. Now we know that sigma is two alphabets, that is A and B. Now the language can accept strings W such that this W has to have even A's and even B's. The order is not specified here. Therefore, we can write AB to the power n. We know that AB to the power n is equal to A to the power n, B to the power n. Therefore, for this question, we can write AB raised to the power 2n, where n is greater than equal to 0. We are not worried about the order in which the characters appear. The only concern is to have even A's and even B's. Okay. Now the first step in the construction of the DFSM is to identify the number of states which are required. And in order to simplify this concept of identifying the number of states, we will use certain terminologies. So first is, how do we identify or represent the strings of the language L? So I will use these notation. In order to represent even number of A's, I will use the notation E of A. To denote even number of B's, it is E of B. Odd number of A's, O of A, and odd number of B's as O of B. These are the 4 notations which I will be using in order to represent the number of A's and B's in the string. We will continue the concept of identifying the number of states. To make this concept simpler, we will consider the following combinations of A's and B's, the input alphabets A's and B's. Okay. We can have even number of A's along with even number of B's. So we know that even number of A's is written as E of A and even number of B's is written as E of B. So this can be our first combination. The second combination can be even number of A's along with odd number of B's. So the second combination which we can have is even number of A's along with odd number of B's. The third combination which we can have is odd number of A's along with even number of B's. Therefore, it is odd number of A's along with even number of B's. And the fourth case which we can have is odd number of A's along with odd number of B's. Therefore, the fourth combination is odd number of A's along with odd number of B's. Now, these 4 cases, we convert them as 4 cases. Okay, this is called as case 1, or I'll call it as case 0. This is case 1, this is case 2, and this is case 3. The order is not of importance to us. We can have order of A's and B's in any format. When we are talking about even A's and even B's, okay, I'll consider A to the power 2, B to the power 2. What are the different combinations we can have in this? We can have AA, BB. We can have B, AA, B. We can have BA, BA. We can have AB, AB. We can have AB, BA, etc. Irrespective, here we know that there are two A's and there are two B's. Okay. So, to convert this concept into the number of states, because we require number of states, we will do this following. So whenever we have the combination of even number of A's and even number of B's, that is our first case or case 0, we will use Q0 as the state representation. When we have even number of A's and odd number of B's, that is our case 1, we will use Q1 as the state representation. Whenever we have odd number of A's and even number of B's, we will use Q2 as the notation. And when we have odd number of A's and odd number of B's, we will use Q3 as our state representation. So having identified the number of states required for the problem, we will go to the second step, that is to identify the start state and the final state of the problem. Now we know that before reading any input symbols, the number of A's and the number of B's will be equal to 0. We are talking about even strings, even length strings. We know that even length strings will be 0 A's, 0 B's. If we are talking about A and B's, it can be 0 A's and 2 B's, 0 A's and 4 B's, etc. So the first minimum string which we have is 0 A's and 0 B's. Now which is the state of 0 A's and 0 B's? This corresponds to even number of A's and even number of B's. So even number of A's and even number of B's is our case 0, and case 0 is denoted by the state Q0, which is the start state. Okay. Next is identifying the final state. Now in the final state, the question is to accept a language which has got even number of A's and even number of B's. So only then we can accept the language. So which is the state which accepts even number of A's and even number of B's? Again, it is Q0 state. Therefore, Q0 state is the final state. Once we have identified the start state, final state as well as the number of states, we go ahead with designing the DFSM. And for designing the DFSM, I will consider the even number series. So we know that even number series starts from 0 to 4, 6, 8, etc. So the simplest of the or the smallest of the even number is 0. In order to write this first transition, I will consider 0 A's. Okay, this 0 A's is actually even number of A's. On this even number of A's, we read an input symbol A. So reading an input symbol A will be plus 1A. Now 1A is added to this even number of A's. So what happens? This results in 0A plus 1A is 1A. Now what is 1A? 1A is an odd number of A. Therefore this transition is on an even number of A state. If A is read, then we result in an odd number of A state. Similarly, on an odd number of A, consider we already have 1A read, we give another input A. what will it result in? It will result in 2a. 1a plus 1a is equal to 2a. Now 2a belongs to an even a series. So we have odd a and 1a to an odd number of a resulting in even a. Therefore, a state OA on receiving A input will go to an even number of A state. This concept is repeated with even B, input B. On an even input state, even B input state, if we are to give another B, so 0B plus 1B, what will happen? It is 1B. So we know that 0B stands for even B. This is plus 1 input which is given. It will result in odd number of B's. Similarly, when an odd number of B's state is reading an input B, it will result in even number of B's. Already it has got 1B or it has read 1B. Now we give another B as the input. It will result in even number of B's. So this is our odd B. It is reading another input B. So it will result in even number of B's. We shall see how state transitions occur in each of the cases. We know that input alphabet is A, A and B, only two symbols. So on each state we have to check the transitions for on receiving each of the input. Now the first state Q0. Q0 corresponds to EA and EB state combination. On Q0 when we are giving an A, okay, when we are giving an A, what changes? Even A becomes odd A. But is there a change in B? No, it remains the same. Therefore, Q0 on receiving A goes to state OA and EB. Okay. The next combination is Q0 on receiving B. Okay, Q0 is EA and EB on receiving B. Only B input changes. Therefore, it remains in EA and goes to OB state. So, which is that state? It is Q1 state. Next, we shall see transitions on Q1 state. Q1 state is represented by EA and OB. Now, we give A on this. It was already even in number. A's were already even in number. When it receives another A or sees another A, it goes to OA state. Whereas there was no B input, it remains the same. Okay. Now Q1 on receiving B. What happens? There is no change in the number of A's, so EA remains constant. Odd number of A's plus another B it sees. So it goes to even number of B's state. That is Q0 state. Similarly for the other transitions. On Q2, that is OA and EB state. When it receives an A, it ends up into even number of A's. There are no changes in the number of B's. Therefore, when Q2 state sees an A, it goes to Q0 state. Q2 on seeing a B. There is no change in the number of A's, whereas even number of A's on seeing another B becomes odd number of B's. So OA and OB is Q3 state. Next is state Q3, which is represented in the combination OA and OB. On receiving A, odd number of A's, it becomes even number of A's, whereas there is no change in the number of B's which it sees. So it goes to EA-OB combination, that is Q1 state. And Q3 on receiving A, on receiving B, which is OA and OB combination. So there is no change in the number of A's, but we have a change in the number of B's. It goes to OA and EB combination, that is Q2 state. The quintuple representation for this DFSM is given as Q is equal to 4 states, Q0, Q1, Q2, Q3. Sigma we know is 2 alphabets, input alphabets A and B. Q0 itself is the start state for this question because we want to accept even number of A's and even number of B's. And the start state Q0 itself is the final state in this DFSM. So what are the transitions which we have? A and B are the two inputs. So Q0 is the start state. Q0 on receiving A goes to Q2 state, and Q0 on receiving B goes to Q1 state. Q1 state on receiving an A goes to Q3 state. On receiving a B goes to Q0 state. Q2 on receiving an A goes to Q0 state. On receiving a B goes to Q3 state. And Q3 state on receiving a A goes to Q1 state. On receiving a B goes to Q2 state. And Q0 is our final state too. So this is the transition table. The same can be listed out as a transition list. The same question can be asked in different formats. Now here the statement of the question was to construct a DFSM to accept strings of A's and B's having even number of A's and even number of B's. So this is one way of asking the question. The second way of asking the question can be construct a DFSM to accept strings of a language which consists of strings W such that W has got even number of A's and even number of B's. The third way of asking the question is to construct a DFSM to accept a language which consists of strings of W such that number of A's in W and number of B's in W are divisible by 2. Fourth way of asking the question is number of A's and number of B's in W are multiples of 2. And the fifth way of asking the question is by making use of the term mod, where number of A's in W mod 2 is equal to 0, number of B's in W is mod 2 equal to 0. So there are different ways in which the same question can be asked. So in case we want to change the question as even number of A's, so even number of A's and odd number of B's, then which state becomes the final state? The Q1 state. Okay, this is a DFSM. This figure is a DFSM to accept even number of A's and odd number of B's. The only change is in the final state. Suppose we are talking about odd number of A's and even number of B's. Odd number of A's and even number of B's. This is the accepting state. So OA and OB, OA and EB, that is Q2 state, becomes your final state. And in the case of a DFSM to accept odd number of A's and odd number of B's, odd number of A's and odd number of B's, this is Q3 state. Therefore, Q3 state becomes the final state. So changes occur only in the final state representation, whereas state transitions remain the same.